Hello, physics students. Welcome to another installment here with planetary motion. We're going to look at universal gravitation. So, Isaac Newton, he hypothesized that there was a force of attraction between any two objects, and it is said that he sort of saw this happening when, or figured this was happening while he saw an apple falling. That's where you get the whole idea of the apple. But here's what he did. He went ahead and he put together a formula that you could use to calculate the force of gravity between two objects. And he hypothesized that the size of the two objects mattered and the distance between them mattered, and that there was a force which was a constant force throughout the universe. And this was just a totally awesome, just out there kind of idea that there was this constant force, and he was able to come up with this idea. He didn't actually ever calculate the force, he just figured it existed. And so he came up with this formula right here, that the force of gravity equals this gravitational constant, and then this would be the mass of one object times the mass of another object divided by the distance between them squared. Now, to go ahead and sort of, think about this, this is talking about something going around another object. So this is like orbiting another object. So you could think of it in the idea of, you could think of it as the idea of circular motion, or what we talked about before as the force of centripetal. So the force of centripetal could be keeping this object moving in a circle. Now we know from Kepler's laws that everything moves in ellipses, but the calculations, if you just figure it based off perfect circles, actually works just fine. So the force of centripetal, we remember, equals the mass times the acceleration of centripetal. So we could say the force of centripetal is going to equal the mass of the planet times the acceleration of centripetal. And so we know that the acceleration of centripetal, based off the time it takes to go around, which would be like a full orbit or full period, is 4 pi squared r divided by the time squared. So we could take force of centripetal here, and we could insert the acceleration for centripetal, or what the period is right here. And we could say that the force of centripetal equals the mass of the planet times 4 pi squared r divided by the period squared. And since force of centripetal and this is the same force, then this right here, if you're talking about a planet revolving around the sun, so I put an S right here and P for planet right here, then this right here equals this right here. So then you could take that, and if you were to rearrange these two equations, this equaling this, to isolate time or period, you could solve for the period of any planet rotating the sun using this equation right here. Time the period equals 2 pi times the square root of the radius cubed divided by the gravitational constant times the mass of the sun. So if you were to go ahead and do the algebra to derive that, that's what you get. But just to kind of show you where this comes from and how all of these things are related in the idea of the planets, because the planets are obviously doing circular motion, but we have forces, and we have force of gravity holding them because they're not held by any strings or contact forces. So what about this idea of G? Now G equals 6.67 times 10 to the negative 11th. Now that number right there, Newton didn't come up with it, and later on a guy named Henry Cavendish actually used a device. I got a picture of it. I've got a picture of it right here. And he used this device right here, and what he did was he suspended two small balls that were on a rod like this, and those were suspended from a string so they could rotate very easily. They're very sensitive then to any force that acted on them. And then he put these ones in a fixed locations, and these were larger balls. And then as he put them in close proximity to each other, the force of gravity would actually attract these smaller balls to the bigger ones. And so then he was able to figure out the force of gravity because the point at which there was enough resistance to stop these balls from going towards each other was actually, the force of gravity. That's what it took to equal the force of gravity. And he was able to measure that by shining a light right here, which then went on a scale. So anyways, using this light reflected off this mirror, as this turned, it would turn the mirror, which would then move the light down this scale. And so he was actually able to get some measurements from these turning rods. So amazing little contraption, but he actually figured out this number right here. So then this is it. This became the gravitational universal constant. He got it right, at least close enough to make a lot of predictions and do a lot of really cool physics on the planets. So in all of this, here's a few things that you want to keep in mind for the rest of like the problems. We'll do a few practice problems. This equation right here, the value of g, knowing the force of centripetal equals the mass of planet times the acceleration of centripetal. Remember this equation right here. Remember this one for solving for the period of a planet going around the sun. And then also realize that the force of gravity, right? The force of gravity, which we know equals the mass times acceleration. That's also what this equals. So this force of gravity, this is force of gravity right here. So this mass times acceleration is also going to equal this g times m1 times m2 divided by r squared. So and to further point that out, this would also be in the case of friction problems, this would also be force normal, right? Because force normal equals mass times the acceleration of gravity. So so this is a really far-reaching sort of concept, and there's a whole lot that you can do with it. So stay tuned. We're going to do a couple problems in the next couple ones. I'm going to use this law of universal gravitation to show and prove some acceleration and some friction problems, and kind of show you a few different kind of neat things that you can do with it.